then we'll start reviewing and go over any questions you have from Chapter 8 or Chapter 9. And talk about the exam that's looming. So we are dealing with differential equations, and let's just recall that we're dealing with differential equations that are separable. And so our goal at this moment with this type of differential equation, which is kind of the first type of differential equations that you study in any course, the idea is that you want to have all the y's on one side and all the t's or x's on the other. And when we say all the y's and all the t's or all the x's, we also mean the differential. And we want to keep in mind that the differential can't be square rooted. The differential can't be squared. It can't be in the denominator. So we always are targeting the differential being in the numerator on each side. All right, so that allows us to integrate each side once we have all the variables separated. So that's kind of our primary strategy here for these. And the ones that we solved up until this slide, we could always find an explicit solution. And explicit means that you could solve for y. You could explicitly say y is equal to this, hands down. Right? There's no ambiguity. When you have an implicit solution, you'll see that there's some ambiguity. So let's go ahead and do a couple of these that have implicit solutions. We still start out, when we deal with differential equations that are separable, we still start out by turning the prime notation into differential notation. So that's always the first thing we do. In order to separate, we need dy dx or dy dt, whatever the variables are. Y is the dependent variable, and t is the independent variable in this case. And this one is fairly easy to separate. We can multiply both sides by y squared plus 1. Multiply both sides by dt. It is now separated. All the t's, including the dt, are on the right. All the y's, including the dy, are on the left. So that is separation. Once we separate, we integrate both sides with respect to the differential that's on that side. So left side is with respect to y. Right side is with respect to t. And then we do our integration. So we have 1/3 y cubed minus y equals 2/3 t cubed plus a constant of integration. So that is a general solution because there's a constant of integration in there. And it's an implicit solution because we haven't solved for y. One thing we can do here, we could at least clear out the fraction just to clean it up a little bit so that we don't have any fractions. Not having fractions is generally looked upon as a good thing. So multiplying by 3 clears the fractions, and that constant, when it's multiplied by 3, again, we can think of it as just absorbing that multiplication by 3, so we'll still call it c. So this is implicit, and it's general. And there's no way that we can solve this for y. There's no strategy that we know that we could rewrite this and isolate y. If we factored out a y, we'd have a y squared minus 3. We could divide that to the other side, but we still wouldn't be able to split it and somehow collect like terms and isolate y. So this is as good as it gets for the general. We cannot isolate y here. So all we can do is present an implicit solution. No other choice. The initial value that they give us, let's go ahead and fiddle with that. They say that when y is 0, t is 0. Well, that gives us that c is 0. So therefore, the particular solution, the solution particular to this initial value, is right there. So this is an implicit particular solution. And that's as good as we can do. Now let's just take a look at a graph of this implicit solution. So we can pop this into Desmos and just get a sense of what it looks like. Let's see. So we'll write this as y cubed minus 3y. In Desmos, we'll write it with an x instead of a t. And that should be a cube up there. So there is the solution. So that is the implicit solution. So let's talk about this implicit solution for a moment. So when we look at this implicit solution, this graph right here has 3 distinct functions. So this curve is called a relation. It's not a function because it doesn't pass the vertical line test. But implicit in this curve are 3 functions. There is the function that starts about there and goes out that way. There is the function that is right there. And then there is the function that is down here. So within this curve, there are 3 functions. Sometimes the relation is nice enough that you can actually identify an explicit solution like we talked about on Thursday. If you have a circle, this circle is not a function, it's a relation. But if you wanted the equation for, say, the lower half of this circle, you could find an explicit representation of the lower half or the upper half. So sometimes a relation can be broken apart into its component functions. That curve cannot be broken apart into its component functions. You will not find y equals blah, blah, blah for the green, the blue, or the black. Can't do it. It's not going to be possible with this to find explicits there. Now what we can do is say that only one of those 3 satisfies this initial value. That initial value is right here. So the curve, if we could separate this into, say, a y1, a y2, and a y3, the curve would be that y2. It would be that blue curve. But there's no way to do that here. So the best we can do is say that this is the implicit solution, and if you look at a graph, it's going to be that right there. That's the solution. So that's what it means to have an implicit solution. We just can't isolate y and get an explicit representation of the function part of the relation that satisfies the initial value problem. Okay. So we cannot isolate y. So we leave it as implicit. So let's take another one. So again, we have something presented to us in prime notation. We're going to switch it over to differential notation right out of the gate. That's the only way we can separate, is to turn it into differential notation and then put the y's on the left and the x's or t's or whatever the independent variable is on the right, in this case x's. So this, again, is not too bad in terms of separating. All we're doing is multiplying the dx to the right and multiplying that y expression to the left. Now we can integrate. Now on the left, you could use u substitution if you wanted, or you could just multiply it all out and use the power rule. U substitution would work here, but it's kind of silly. It's going to be a little easier just to multiply it all out and use the power rule. If you were going to use u sub, what would you let u be? Yeah, 2 plus y squared right there. Its derivative is 2y, which will pick up right there. So you could use u sub there. It makes more sense, though, just to multiply this out. This will be y to the 4th times y, which will be y to the 5th. The middle term will be 2. So 2 times y squared doubled, so 4y squared, but then you multiply by y, so you get 4y cubed. The constant will be 4, and then you multiply that by y, you'll get 4y. So that is our left-hand side, and there's our right-hand side. Both of those can be integrated. So over here, we'll end up with 1/6 y to the 6 plus y to the 4 plus 2y squared. Over here, we'll end up with x squared, and we'll put our constant of integration on the right. You can think of each side as having its own constant of integration, but then they get combined into a single constant, which we'd normally put on the right. All right, once again, we have a fraction. Let's clear the fraction. Is it necessary? No, it's not absolutely necessary to clear the fraction. But clearing fractions is just a nice thing in terms of writing your final answer, having no fractions, if possible. Do you think you can isolate y there? No way. There's no way that you're going to be able to isolate y and get y equals. Right? You have all these even powers. If you had some odd power, if you had an odd power and nothing else, if you had a single odd power, obviously you could isolate y. If you had a single even power, you can't isolate y. You can't isolate y if you have even powers, ever. You might say, let me just make sure this is clear, if you say this, that is not isolating y. When we say isolate y, we mean that y is equal to one and only one expression. So here, when you say y is plus or minus y, plus or minus the square root, you haven't isolated it. I mean, it looks isolated, and it's isolated in kind of an algebraic sense, but in a differential equations function sense, this is still one or the other. It's not a single. To be explicit, there cannot be any ambiguity. It can't be plus or minus. That's ambiguous. So to be explicit, we have to be able to get down to y equals something definitively, not plus or minus. So this will not happen. You can't do it there. You can try, but there's no algebraic technique that will work. So this is our implicit general solution. And then once again, they gave us y of 1 is equal to negative 1. So if y of 1 is equal to negative 1, let me keep that on the board. Let's go over here. Y of 1 is negative 1. So this tells us that when x is 1, y is negative 1. So let's plug that in. So negative 1 for the y value, raised to the 6th power, positive 1. So on the left, we'll end up with 1 plus 6 plus 12. On the right, we're plugging in a positive 1. We get 6 plus c. So we will get c equals 13. So therefore, our particular solution for this initial value, let's see, that's a y, plus 12y squared equals 6x squared plus 13. So that is our particular solution, but it is implicit. We cannot find an explicit. So this is implicit. and it's particular. And there's no way to isolate that y. So once again, we can look at the graph of that particular solution. We can graph it in a graphing utility, and we can get a sense of what it looks like, but we are not going to be able to come up with an explicit answer. We can't come up with a y equals plus 12y squared. Yeah, question.
So on the test, whenever we're doing differentials like this, are you going to expect us to get rid of the fractions kind of like you are?
No, if you don't get rid of the fractions, I wouldn't take any credit off.
Okay.
Yeah, no. And obviously, I can't put one of these on the test because you're not going to have a graphing utility, so you couldn't like do the graph. You could write the explicit, or you could write the implicit answer, but you couldn't do this part here.
Okay.
So this part would be not possible for the test. So this is a lot like the circle one we just talked about. You can really look at that and say, okay, it's the bottom half, but you can't isolate it. The circle you can isolate and get that the bottom half is this explicit expression. Here it looks very similar. There's a top half and a bottom half, but we can't isolate with that equation. So is the answer, let's see. So x is 1, y is -1. That is right here, 1, -1. So the answer is this curve right here. This is the answer, but we can't write it in any sort of explicit way. All we can say is that, implicit. All right, any questions on those two examples? Yeah?
So the implicit particular kind of form is just telling us a point on the actual graph of the function.
So particular means that you have some initial value. So that allows it, because right now when you get your general, there's a plus c. That means there's an infinite number of curves right here. This is one curve. This is one curve. It's a disconnected curve, but it's still considered one curve, right? That's the graph of this single relation. This has an infinite number, so there's going to be a whole bunch of, so each curve in this case looks like a pair, and so there's going to be an infinite number of pairs of curves. This one particular curve is the solution for this initial value problem. So just like a regular antiderivative has an infinite number of curves, right? When you do an indefinite integral, you always have that plus c. You have an infinite number of antiderivatives. Same idea. If you're given a value, then you can find one curve that satisfies that value. That's the particular antiderivative. So it kind of narrows it down to one curve. And ideally, you can find the answer explicitly, but often you can't. Often you can't. So let's do one more. So why don't you all try this one? So separate it and see if you can find an explicit solution. Let me know if you're stuck and need a little nudge.
throw me off.
Let's find out what the negative sign is doing. So up here on the board, that's the separated version. And once we have everything separated, we go to the integral. And then we're integrating in this way. Multiplying by 2 clears out the fractions, which we prefer. And here's where we can say, oh, constant multiplied by 2 is still a constant. We'll just keep it as a c. And then normally we would write this probably as x squared plus y squared equals c. So here is our general implicit solution. We cannot isolate y there in the explicit sense. We could write it as y equals plus or minus the square root of c minus x squared, but that's not helpful. So our initial value says y of 0 is 4. So if y of 0 is 4, our particular solution, we're going to replace the x with 0, the y with 4. We're going to get a constant of 16. So therefore, our implicit particular is that. Well, we know what that is. That's a circle of radius 4 centered at the origin. So we know that we are dealing with this object. And we know the location of this initial value. Y of 0 equals 4. That says when x is 0 and y is 4. So this is the implicit function that we're looking for. And because this implicit function is coming from a relation that we can break apart, we can find the explicit form of that implicit function. So let's see. That is going to be the top half of this circle. So here is going to be the explicit solution. So in this case, we can find an explicit particular. So that is explicit, and it's particular. So unlike the prior two, we could look and see our implicit function, but we couldn't come up with an explicit form for it. So we had to leave it implicit. Federico?
How would you know that your explicit solution is the positive half and not the negative?
Because the initial value tells us a point that is on the curve. So this tells us that the implicit function must be the implicit function that goes through 0, 4. Yeah. Chapter 9 in the books. Done. So we don't cover a lot in Chapter 9. It's a fairly easy part of the exam. You know, it's nice that it comes right at the end. It's not like the hardest stuff right at the end. So let's go to the review stuff.
Can you
Ryan?
put the label on there, like the x squared plus y squared equals c? Is that that's the implicit general, right?
That's the implicit general. That's correct.
And then the x squared plus y squared equals 16 is the implicit 4.
General. And then this is the implicit particular. And then this is the explicit particular. Yeah. All right. Any Diffie-Q stuff from 9.1 or 9.3 that you want to talk about before we start reviewing? Cameron?
Can you do some like tricks with like tangents?
Yeah, we will definitely do trig sub. Let's do it. Let's go to our review page. We'll get to the trig sub. Let's go in order, because that's helpful. So same old rules. No graphing calculator with no graphing calculator or no calculator with an integral button. It's just not fair if some of you have an integral button and some of you don't. because if you have an integral button, you can check your answer. So no integral button calculators. No phones, no note cards. And then here are topics. So let's start back here in 8.1. 8.1 was the section that I sort of got the most questions on because 8.1 doesn't have definitive processes.
That was my issue with it.
Yeah, that's everyone's issue with it. It's like, wait, where do I start? When someone says use trig sub, okay, you know where to start. When someone says use integration by parts, you know where to start. When someone says, integrate that, that one's pretty obvious. But these ones that are a little less obvious, unless you're told exactly what to do, it's not obvious what to do. So let's talk about those. So let's not do this first one. Let's just talk about it though. We'll use the power rule. We add 1 to the exponent, getting -3. Divide by -3. And then what will be the reverse chain rule piece? Divide by 2. So the quantity in the parentheses has a derivative of 2. So the reverse chain rule part will be a division by 2. All right, so negative exponents. So our strategy with negative exponents is to eliminate the negative exponents. And remember that the book calls this subtle substitution, which is very misleading. If you see negative exponents, we just want to eliminate them. And what we will do is multiply by a form of 1. And so we are going to multiply by e raised to a power. And what power would we choose? 4x. If we multiply by the reciprocal, let me make sure that you're understanding that this is the reciprocal. Do you agree that e to the 4x and e to the negative 4x are reciprocals? What are reciprocals? They multiply to 1. That's what reciprocals do. 3 1/3 are reciprocals. They multiply to 1. 5 1/5 are reciprocals. They multiply to 1. If you multiply e to the 4x times e to the negative 4x, this is equal to e to the 0, which is 1. So those are reciprocals. So you take the exponent, make it positive, and all of a sudden you have your reciprocal. That makes sense? The reciprocals always multiply to 1. Okay, so here, what will we be left with in the numerator? E to the 8x. If we multiply exponential expressions with the same base, add the exponents. All right, and then down below, we're going to have an e to the 8x over on the left minus 3. Because e to the negative 4x times e to the 4x is 1. 1 times 3 is 3. And then where are we going to go from here?
U sub.
We could go to u sub. There's a faster way, though. What form? Log form. The derivative of the denominator is e to the 8x times 8. So we would want to do a little bit of manipulation, tweak it a little bit, multiply by 1. Now it's in log form. So if we did u sub, we would let u be the denominator. We'd still get the division by 8 with u sub. But it's a little quicker if we just put it in log form. So remember that log form is when the denominator's derivative is exactly the numerator. And the derivative of an exponential is itself times the derivative of the exponent. The derivative of this exponent is 8. Derivative of 3 is 0. So now that it's in log form, we can write down our answer. The answer for log form is always natural log absolute value of the denominator plus c. All right. Stop me if you have questions. why would we not use PFD for this one? Why would we not use PFD? Because we cannot factor the denominator. So if you have a quadratic in the denominator and you can factor it, then you would go to PFD. If you have a quadratic in the denominator that you can't factor, you complete the square. Right? So that's our triage process. If you can factor, you know that you would go to PFD. We can't factor, so we're going to complete the square here. And to complete the square, we're focusing on just these x terms right there. We take the coefficient of x, divide by 2 and square, and we get a 1. So we're going to have x squared minus 2x plus 1. We can think of taking that 1 out of the 50, so the 50 is now turned into a 49. So now we've completed the square. And that allows us to write the denominator as a sum of squares. This is what you wanted, Cameron. Sum of squares. All right, it's almost in the form that we want it in. What do we do to put it in that? Yeah, say again?
7 squared?
But we want to make that a 1 if we can.
Oh,
So we're going to factor out the 49. So if we factor out that 49, that's in the denominator. Notice there's no power, right? We don't have like a big square root under here. If there was, then a 7 would come out. Or if there was a big power of 2/3 or something, then the 2/3 power would come out. So whatever the power is has to come with it. But there's no power there. So 49 comes out as it is. So then we have dx divided by, so that's a 1. And there is no 49 over here. So if we want to, we can think of putting in 49 over 49. That's 1. And these two 49s are the ones that factor out to that. So we want to write this leading term here as a square. So that'll be x minus 1 divided by 7 squared. That is now in arctan form. So if we wanted to use trig sub, we could, but we don't need trig sub actually because it is in arctan form. We know that the derivative of arctangent of u is 1 over 1 plus u squared times the derivative of u if we needed to. Right, so that is in arctan form. So the integral of this, we can cut right to the chase. This will be 1 over 49. I'm going to leave a gap for the reverse chain rule. It's just arctangent of whatever is in parentheses. And then what are we going to put in the RCR spot? 7. Because the derivative of this, the derivative of x minus 1 over 7 is 1/7. And dividing by 1/7 is multiplying by 7. And then we can do a little bit of simplification there. That'll be 1/7 arctangent. And that's as simple as we can go. So that'll be our. Now if we did go with trig sub, that's fine. And I should put a prime on this. This is a derivative here. Derivative. If we didn't see that it was in arctan form and not trig substitution, you would still get to the same answer. Whenever you use trig sub when you could have used an immediate arctan antiderivative, you'll end up with an integral of d theta. If you end up with an integral of d theta, which will be theta, that's sort of like, oh gosh, that means I could have done it directly. But trig sub will work. You would let x minus 1 over 7 be tangent. Parts? what would we let you, what would we let you be in this case? X. And let dv be e to the 4x. Do we need to go through that? Done enough of those? So let me just write down that we would let u be x, and if you try it and you can't get to it, just let me know and I will help you. So that would be our setup. Integration by parts with a twist. So hopefully you're seeing by now that we get this twist when we have two functions that differentiate or integrate cyclically. Right? The derivative of sine is cosine, derivative of that is back to sine, so it's sort of cycling between sine and cosine, and e to the x cycling between e to the x repeatedly. That's when we're going to get the twist thing. So let's go ahead and do one with a twist. And the nice thing about the twist is that it doesn't matter which function you choose for u and which function you choose for dv. It's not going to matter. So if you are doing integration by parts with a twist, and you're trying to decide which should be u and what should be dv, it might be that you find differentiating trig easier than integrating trig. And if that's the case, then you should put the cosine, the trig, with u. If it's easier for you to differentiate trig than integrate trig, put the trig with the u. If it doesn't matter, then it doesn't matter. So whatever works best for you. So I'm going to put it, I'll just do it in the order that it's there. I feel okay integrating trig. So then we'll differentiate. So we're going to have du equals 3e to the 3x dx. And when we integrate, we're going to integrate cosine to get sine of the same angle. And then what's the last piece? RCR divided by 2. So there is our first integration by parts. And typically we're going to call this integral something so that we can refer to it very easily and not have to rewrite it a bazillion times. So we'll call it omega. And this will end up being u times v. So that's 1/2 e to the 3x multiplied by sine of 2x. So right now I'm multiplying this main diagonal right here. There's uv. Minus the integral of v du. So v du is this way. And here's where you have a choice. There's constants involved. You could pull the constants in front of this integral, which is fine. I'll leave them on the inside because if you pull them on the outside, you're going to have some big brackets when you do your next integration by parts, and you'll have to remember to distribute them, which is fine. But I find it easier just to keep them all inside. When we multiply v and du, both these are positive. So they multiply to positive, so that means this negative here is just going to stay. So we'll have a 3 over 2. We'll have an e to the 3x, and we'll have a sine of 2x. There we go. Now we do our second integration by parts, and we want to be consistent. So if we let u be exponential, we let u be exponential. So I'm going to put the 3/2 with the e to the 3x. du will then be 9/2 e to the 3x times dx. dv will let dv be the trig portion of the integrand. So v will be, we integrate sine 2x. What will we get when we integrate sine 2x? Minus cosine of 2x over 2. All right. So again, we're going to do this main diagonal minus the bottom row. So same thing. We need to be cautious here we have a minus sign that is out in front of this integral that we're about to turn into integration by parts. So normally we have uv minus integral of v du. If there's a leading minus, then that minus distributes so that we'll have minus uv plus the integral of v du. So let's be careful with that leading minus sign there. So when we look at u times v is negative. So that's going to change the sign right here to positive, and we're going to end up with 3 over 4 e to the 3x cosine of 2x. And then plus the integral of v du. So plus the integral of v du. V du happens to be negative, so that becomes minus the integral of 9/4 e to the 3x multiplied by cosine of 2x. All right, any questions on the signs or the coefficients or the integration by parts tables? So over here on the right, what we notice is that the integral over there is exactly like the original integral. So we are going to write it as a multiple of the original integral. So we're going to write it as a multiple of omega. So that will be minus 9/4 omega. Everyone okay with that? Like when we look at omega, omega is the integral of e to the 3x times cosine 2x. So here, if we factor that coefficient out, we just have negative 9/4 times the original integral. And now we are back to algebra. On the left, we have an omega. We have 1 omega. Let's write that 1 omega so that it has the same denominator as the omega on the right. Write it as 4 over 4. 1 omega. It'll be easier to add. So when we add the omegas together, when we combine like terms, we are going to have that. And what? I guess I have to use my finger. Okay. So then we have to change that to a plus c. As soon as we add that omega to the left, we need to put a plus c. Why? Because omega is an indefinite integral, and we know that once we integrate that, we will have constant of integration. So we want to make sure that we get that constant of integration on the right. And now our last step is to isolate omega. So we multiply both sides by, 4 over 13. 4 over 13. By the reciprocal. Reciprocals multiply to 1. So we multiply by 4/13. 4/13 times 13/4, 1. So 4/13. 4 is going in the numerator, so this is going to be 2/13 e to the 3x sine 2x. And then 4/13, 4 is in the numerator. 4 will cancel with the 4 in the denominator, so we have 3/13 e to the 3x cosine 2x, and a constant times c is just a constant. So that is the indefinite integral of what we started with. A whole family of antiderivatives. Make sure you can do integration by parts with a twist. Any questions on the twist? Hopefully we've done enough of them that you can redo that on Thursday. Find the volume that is generated when the region bounded by e to the negative x and the x-axis is revolved around this line. Please be able to graph e to the x and e to the negative x. Those are basic exponential graphs that you should be able to graph without even thinking twice. So e to the negative x is an exponential decay, and it goes right through the point 0, 1. Right, that's what e to the negative x looks like. Horizontal asymptote, x-axis. So that is y equals e to the negative x. So we find the volume of the solid generated when the region bounded by. So let's find the region. There should only be one. There should be no ambiguity. So this is one of the boundaries. Okay, they tell us it's on the interval 0 to natural log of 6. So we're going to call this natural log of 6 right there. And they tell us that the region bounded by that, the x-axis, on the interval. So that interval is giving us kind of the lateral bounds. They say it's on the interval 0 to natural log of 6. So that gives us the sides. So this whole region here, there's our region. And we're going to rotate around y equals, or x equals, natural log of 6. So here is our axis of revolution right there. So we're going to rotate around that. Okay. And it says to use a shell method. Is it obvious that we would not want to use a disk method here? If we were going to use a disk method, the element would have to be perpendicular to the axis of rotation, and we don't have a unique left boundary. Let me restate that. We don't have a unique right boundary. If we drew our horizontal element right there, the right boundary is that. If we drew the horizontal element here, the right boundary is right there. So we don't have a unique right boundary, so it makes no sense to try to do a disk. So we're going to draw a vertical element, and that is why we'll use a shell, because that is parallel to the axis of rotation, which creates a shell. Okay, so now we know that for a cylinder, the area of a cylinder is 2 pi r times h. It's the circumference of the base multiplied by the height. So 2 pi r h. We look, this is the vertical element at a random x. The radius is the distance from your element to the axis. So there's the radius. That is a horizontal distance. Anytime we do a horizontal distance, we do the right x value minus the left x value. The right x value is what?
Natural log of 6.
Natural log of 6. That's the right x value. The left x value?
X.
X. All right, the x on the left, natural log of 6 on the right. So that difference is natural log of 6 minus x, not x minus natural log of 6. If you're doing horizontal subtraction, you have to do the bigger number minus the smaller number, right minus left. And this x is to the left of natural log of 6, which means it's smaller than natural log of 6. So it's right minus left to get distance. And then the height is whatever that vertical distance is. And what is that vertical distance?
E to the negative x.
E to the negative x. That function is e to the negative x, and that function measures the distance from the x-axis up to the curve. So that is our setup. So volume will be the integral of this from 0 to natural log of 6. The 2 pi can come to the front. We're going to distribute. We're going to have a natural log of 6 multiplied by e to the negative x, and we're going to have a minus x e to the negative x dx. So there is our setup. we have two parts to this integral, two terms. That left term has an immediate antiderivative. It's just a constant multiplied by e to the negative x. Constant, of course, can be ignored when you integrate here. So that's immediate. And then what technique do we have to use for x e to the negative x? Integration by parts. We have a product. And when we have a product, we use integration by parts unless u substitution happens to work. So this is going to be 2 pi multiplied by a bunch of stuff. This we can integrate instantly. So we have natural log of 6. The integral of e to the minus x is itself multiplied by minus 1. So I'll put a minus right out there in front. That's going to be evaluated on this interval from 0 to natural log of 6. And then minus, let's get the integral symbol over here, and then we'll do this integration by parts separately. So we have x e to the minus x dx. And then I guess we could use a parenthesis here instead of a bracket. All right, so that's where we're at. We could evaluate that first expression, 0 to ln 6 if we want, or we could just wait and evaluate at the end. Doesn't matter. I'll just wait. Let's do our integration by parts setup over here. We're going to, once again, you already told me earlier that we would let u be x for this type of one. So there's our setup. du will equal dx, and v will be negative e to the negative x. So 2 pi, big parentheses, negative natural log of 6 e to the negative x. We're waiting on the evaluation there. So minus uv is negative. If uv is negative, then that's going to combine with this minus and turn it into a plus. So we're going to get plus x e to the minus x. And all this stuff in front is going to be evaluated on the interval 0 to ln 6. So uv minus the integral of v du. But we already have a minus in front of that, so it's minus a minus, which makes that plus. And then we look at v du, and oh gosh, v du is negative, so then it switches again to a minus. So we've got 3 minuses there. So we're going to have minus integral e to the negative x dx. All right, so then we can integrate that immediately. We know the antiderivative there. And we'll just do all of our evaluation all at once. All right, any questions before we evaluate? Any drama in your head related to this? All right. We'll plug in the ln of 6 first. So we have 2 pi multiplied by. All right. I'm going to come over here to the side. If we have e to the minus ln of 6, what does that simplify to? 1/6. Do we see it? So that minus in front flies up to the top, right? That's a coefficient, so it flies up here to it as a negative 1. So we'll have e to the ln, which those cancel. And we have 6 to the negative 1, which is the reciprocal of 6, which is 1/6. So in here, this is going to be minus natural log of 6 divided by 6. E to the negative x becomes 1/6. And then here, plug in natural log of 6. So again, we're going to have natural log of 6 divided by 6. Because e to the negative natural log of 6 is 1/6. And oh, here it is again. So there is the upper endpoint plugged in. And then we subtract off the antiderivative at the lower endpoint. Plugging in 0, e to the 0 is 1. So we have minus a minus, which makes plus ln 6. And then minus 0. Plug in 0 there, we get 0. And minus e to the 0, which is 1. So that'll be the evaluation. We have some cancellation. Negative, positive, those go away. And we'll end up with 2 pi multiplied by negative 5 over 6 plus natural log of 6. Which we can just leave it like that. You could distribute the 2 pi if you want. You could do a whole bunch of things. We'll just leave it like that. Good. Let's take a 10-minute break. If you have any questions on this, come and ask. All right. The simplest powers of trig functions are sines and cosines. And with sines and cosines, you only have to remember that if a power is odd, you pull one off and convert the leftover ones. And so that's a lot less thinking than the secants and tangents. The secants and tangents are a lot more complicated. But sines and cosines, if you see an odd power, you can pull one off and convert the leftovers. So for here, all we're going to do, we can factor the 4 out. And the power on cosine in this particular case is odd. So we're going to pull off one cosine and put it over with the differential. So it's kind of sequestered over there. And then we are using the cosine with the differential thinking that we'll let u be sine because then sine's derivative will be cosine over with the differential. So we want to have only sines left over here. So we're going to replace the cosine squared that's remaining after you pull off one cosine. That cosine squared will be 1 minus sine squared. Okay, so now we're ready for our u sub. So u sub, we're going to let u be sine of x. Derivative of sine is cosine. And so all of these ones with sines and cosines, they unravel really fast if you have an odd power on that cosine. So then this will be 4 integral u to the negative 3 halves times 1 minus u squared du. And what's our strategy now? We're going to multiply that across. We'll distribute it so that we can have a couple of powers and integrate those powers independently. So what is going to be the power on the second term? U to the positive 1/2. Because we add the exponents when we're multiplying powers with the same base, so negative 1/2 plus 2 is positive 1/2. And then we can integrate this term by term using the power rule. We'll have 4 times, that's going to be u to the negative 1/2, adding 1, divide by the new exponent. So we're dividing by negative 1/2, so that's multiplying by 2. And then here we're going to get u to the 3/2 times 2/3 plus c. All right. Anybody have a question on where we're at? So then all we have to do is convert back. Since u is cosine, we are going to end up with, oh, it was u sine? Thank you. U is sine. So this is going to be the square root of sine in the denominator. All right, so that's going to be, let's put that underneath this 8. So square root of sine in the denominator. Sine of x, not theta. And then the 4 is distributing to the second part, so that's going to be minus 8/3 sine to the 3/2 power of x plus c. And that's it. If you left it as minus 8 sine to the negative 1/2, totally fine. Would not take off if you didn't get rid of the negative exponents. Usually we get rid of them, but still correct. All good? Is that a yes? Yes. All right. Powers of tan and secant are more complicated. So powers of tan and secant, we have to think about secant with an even power or tangent with an odd power. So this one actually has both. It has tangent to an odd and secant to an even. So let's talk through both of those. If secant is to an even, we're pulling off secant squared with the foresight that we're going to let u be what? Tangent. If we sequester a secant squared over at the side with the differential, we want u to be tangent so that derivative of tangent is that secant squared. So if we pull off secant squared, how many secants will be left over? 2. And so we could convert those easily with the Pythagorean identity. If we go with the odd power of tangent, we pull off a sectan, thinking that we're going to let u be secant, because derivative of secant is sectan. So if we pull off a sectan and put it over here, how many tangents would be left? 4. Is it easier to convert 4 tangents or 2 secants? 2 secants. That's going to be easier. So that'll be the strategy that we use. If you did it the other way, it would work fine, but it would just be a little bit more work. So if we pull off secant squared and put it with the differential, so there's our differential. Our goal is to let u be tangent. We're left with secant squared right here. Let's draw our triangle, make sure that we're remembering. If this is theta, this is tangent of theta, this is secant of theta, if that's a 1. So how do we replace secant squared? Tan squared plus 1. So now we've done our conversion. Now it's ready for u sub. We're going to let u be tangent. And again, we pull off secant squared so that when we differentiate tangent, there it is right there. There's our du. So our du will be secant squared of x dx. So this all becomes 7 on the outside, u to the 5th, and then tan squared plus 1 is u squared plus 1 du. And similar to the last one, we distribute and use the power rule. So once you've done your substitution, they all kind of unravel pretty nicely. It's just choosing the right substitution. That'll be our antiderivative. All good? All right. So this one, there's only one choice. What would we want to pull off? Yeah, we want to pull off secant squared and convert the secant squared that's remaining. So same strategy actually on that one. Trigonometric substitution, here we go. Never. The only time a trig sub problem is short is if you did it wrong. Trig sub is just, you know. So think about that when you're taking the exam. If there's a problem that you know is difficult for you, don't get tangled up in it. Make sure you, when you're choosing and you're writing down your work on separate paper, you know, you don't feel like you have to go in order. If the trig sub is something you know really well and you just want to get it out of the way, great. If it feels like something that could tangle you up, put it off to the end. You know, be strategic. So the trig sub, of course, the idea is that we want a sum or difference of squares, ideally with a 1. That makes things a little bit easier. So if we factor out the 196 here, that 196 is going to come out as the square root of 196. So that's 14 squared. Square root of 14 squared is 14. So we'll have 1 over 14. What is going to be left over here inside these parentheses that are squared? X over 14. X over 14. And now we're set for trig sub. Let me ask you this. What about if there was no x squared up there, if that was not there, would we still need trigonometric substitution? No, because it would be in inverse sine form, and we could immediately integrate to inverse sine with reverse chain rule. Right? Because that is the inverse sine antiderivative. We would just immediately get inverse sine of x over 14. And would we divide or multiply by 14? Multiply by 14 because the derivative in here is 1/14. Dividing by 1/14 means multiply by 14. So if that was not an x squared up there, we wouldn't need trig sub. Okay. Trig sub, sine, secant, or tangent? Sine. Whoops, u. So we're going to let x over 14 be sine of theta. Derivative of both sides, so we're going to have 1/14 dx is cosine of theta d theta. There is our substitution. So this will become 1/14 integral x squared. So we look to our substitution step, we isolate x. X will be 14 sine theta. And if we square it, we're going to have 14 squared sine squared. If you isolate x, x is 14 sine theta. Square both sides. X squared will be 14 squared times sine squared. And then we have to multiply by dx, which is multiply by 14 cosine of theta. D theta, square root 1 minus sine squared. questions on that substitution? We'll cancel out some 14 here and here. We'll be left with 196 on the outside. Integral 1 minus sine squared. Cosine squared, square root of cosine squared is cosine. So this whole business here, including the square root, and this whole business right there, those two cancel. Because we have a single cosine in the numerator, and in the denominator, 1 minus sine squared is cosine squared, square root of cosine squared is cosine. So we have cosine top and bottom. They go away. All we're left with then is sine squared. How do we integrate sine squared? We're going to power reduce it. So we're going to replace that with 1 minus cosine 2 theta all divided by 2. The division by 2 is a constant, so it can come all the way out to the front. And this will be, what's the integral of 1?
Or theta.
Beta. Theta. So whatever the letter, the variable of integration. Integral of cosine is sine. Reverse chain rule, divide by the derivative of the angle. Bless you. So then, out in front, looks like we're going to have, what, 98? We simplify that. And here we're going to have theta minus sine of 2 theta. Our substitution is with 1 theta, right? Sine of a single theta. This sine of 2 theta business has to go away. So we need to use another trig identity. We know that sine of 2 theta is... Some of you said it. 2 sine theta cosine theta. Double angle for sine. The 2's will cancel with the denominator, so we'll end up with minus sine theta cosine theta. Now we're ready for the cool triangle. Cool triangle coming. So draw this right triangle as if it lives in quadrant 1. And sine of theta is x over 14. So where should the x go? Rise, run, hypotenuse. Rise and run. Rise and hypotenuse. X and 14. All right, so that tells us that's a picture of sine theta being x over 14. Opposite over hypotenuse for sine. Then we have to figure out this side right here. That will be done with the Pythagorean theorem. Hypotenuse squared, which is 196, minus the other side squared, which is x squared. And that should match pretty darn close to something that was in the original. Make sure it does. And now we're good to substitute. From our triangle. Theta, how about theta? Actually, theta, you could get it from the triangle, but it's easier to go right up there and grab theta. Theta is inverse sine of x over 14. So we just inverse sine both sides right here. So so theta will be inverse sine of x over 14. And then minus sine of theta. We can look at our triangle. Sine of theta is x over 14. cosine of theta, look at our triangle. Cosine of theta is the square root over 14. Plus c. So that's our final answer. All we could do is combine those 14s there to make a 196 in that second denominator. Trig sub. Never short. Should we do one more trig sub, Cameron?
Could you go off of it? So, how did you go from, like 196 be at there to the next?
Power reduction.
There's an identity.
So sine squared is 1 minus cosine 2 theta divided by 2.
Is that an identity?
That's an identity that you know.
I know. Is it happening?
Power reduction. The power reduction comes from the half angles. Depends on how you think of it. You can think of it as coming from double angles or half angles, but yeah. Yeah, power reduction. So anytime we have a sine squared or a cosine squared, we have to power reduce before we can integrate. Sine squared and cosine squared, power reduce. One more trig sub. Let's do a secant one. What are we going to factor out in this one to put it in trig sub form? Factor out the 400 is coming out, and what's the exponent going to be on that 400? 3 halves. So it's in the denominator, so we're going to have 1 divided by 400 to the 3 halves power. And then inside, we factored out that 400. There was no 400 in this first term, so it throws a 400 in the denominator. And when we write it as a square, it will be x divided by 20, quantity squared, minus 1. So now we're ready for trig sub. Sine, secant, or tangent? Secant. So we're going to go x divided by 20. U, I declare, are secant. We differentiate both sides. We get a 1/20th dx equals secant tangent d theta. What's the square root of 400? 20. So out in front here we have 1 divided by 20 cubed. Square root of 400, do the square root first. It's easier. And then this is going to be dx. If we look right there, dx is 20 secant theta tangent theta d theta. In the denominator, we have secant squared minus 1, all raised to the 3 halves power. And what is secant squared minus 1? Tangent squared. So we're going to have, and we can simplify this outside number if we want. We can just wait if we want. Doesn't matter. Oh, we can simplify it right now, actually, to 20 squared. There's a 20 in the numerator that will help us out. So let's see. So tan squared, you said. So this is tan squared. And what is tan squared to the 3 halves?
Cubed.
Tan cubed. Power to power, you multiply. So 1 tangent will cancel. We'll be left with 1 over 400. Integral, we have a secant in the numerator. And in the denominator, it looks like a tan squared. That's where we're at. Secant is not to an even power, so there's none of this pulling off secant squared and integrating. There's no obvious way to use a u sub, so probably the best bet is to, say that again?
Trig identities.
We could use trig identities.
By parts.
That would be so mean to put integration by parts into a trig sub already. That would be brutal. That would be so mean. That's a great idea. What a way to go into the weekend. Yeah, don't do u sub. But we could convert to sines and cosines. So if we don't have an obvious trig identity, like if the numerator was tangent squared, so remember that if secant is squared, you pull off secant squared. If tangent is odd, you pull off secant tangent. But if tangent was even in the numerator, then definitely go to a trig identity. But here, the best bet's probably to go to sines and cosines. Because the trig identity that you would pick would have to be for the denominator, and that's going to turn it into multiple terms, which generally is going to make it more complicated. So if we convert to sines and cosines, I'll write tangent as 1 over or secant as 1 over cosine. Tangent squared in the denominator is really a cotangent squared. So that's going to be this. And a single cosine cancels. So we're going to have cosine of theta d theta, sine squared in the denominator. Does u sub work here? U equals sine. Derivative of sine is cosine theta d theta. That is the numerator. So whenever we're doing u sub, we're thinking, okay, does the derivative of whatever we're thinking about for u show up? And it does. It's right there, right in the numerator. So sine of theta for u. So du is cosine theta d theta. So this integral becomes u to the negative 2 du. Which we can integrate, u to the negative 1 divided by negative 1. So it's negative 1 over u plus c. So this will be negative 1 over 400. U is sine of theta. So we'll have 1 divided by sine of theta plus c. Now triangle. We want to get back to x. So let's grab our substitution step from way up here. Secant of theta is x over 20. So secant of theta is x over 20. Draw our cool triangle. Secant, x over 20. Where should the x go? Hypotenuse. Secant is hypotenuse over adjacent. That is our setup. And then our missing side. Square root of x squared minus 400. Go back up and just check. There's an x squared minus 400, so we're probably right on track. So we end up with negative 1 over 400. 1 divided by sine, that's cosecant. And that would be hypotenuse over opposite. Hypotenuse over opposite. Let's see.
Is there ever a time where you can't use like an identity like that, and you have to
This thing here?
No, for 1 over sine at the end there.
No.
Okay.
Yeah, that will. You'll always be able to have sines and cosines here, so you can always go to your triangle. And it really doesn't matter what trig function you end up with. Right? Once you have a right triangle, if you have sines or cosines or tangents or cotangents or secants or cosecants, all of those can be evaluated with your triangle. So you can think of 1 over sine as cosecant and cosecant as hypotenuse over opposite. Or you could say sine is opposite over hypotenuse, but then you have to take the reciprocal of it, so you end up with hypotenuse over opposite. Yeah, but you'll always be able to use that triangle for whatever trig function shows up. Good. Good, good, good. Let's see. Let's do some PFD. How would we know to use PFD here? It's factorable. Yeah. As soon as you can factor the denominator, PFD is a viable option. So factor the denominator. If it can factor, then PFD is going to be a lot better than trying to complete the square and do mumbo jumbo like that. Which would work. You could complete the square and make it 5 times as hard. You could. Not advised, but you could. All right, so the nice thing with this one is that we have linear factors. So those are both lines, mx plus b, ax plus b, however you think of your linear expression. Constant times x plus constant, both of those are linear. So that means we're going to go with an a over x minus 5 and a b over x plus 3. So linear factors are the best because we can use the convenient value method. So we will use the convenient value method as soon as we come up with our PFD equation. Does anyone have any issue getting to that PFD equation? We're multiplying both sides by the left denominator. If you multiply the left by the left denominator, you cancel it, and so you end up with just the numerator. Multiply it by the right, you're going to have a cancellation of 1 factor for each fraction. Now we find our convenient values. And what are the 2 convenient values?
Minus 3 and plus 5.
Yeah. Pretty obvious. And then we run those numbers in. We put them in for x. All the x's you see, replace with -3. Here you'll get 0. And you're going to have b multiplied by -8. So b is going to be -3/8. And then you run the 5 through. When you put the 5 in here, 5 minus 5 is 0, so that goes away. So you end up with 3 equals 8a. So a will be 3/8. So -3/8 and +3/8. So we can rewrite our integrand as, we could just pull the 3/8 all the way to the front. Let's do that. That'll be easier. Let's put a 3/8 all the way out in front. So 3/8 in front. Then we're going to have 1 over x minus 5 minus 1 over x plus 3 dx. Now we can integrate. They're both in log form. The derivative of x minus 5 is 1, which is the numerator. Derivative of x plus 3 is 1, which is the numerator. So they are in log form. So we get natural log absolute x minus 5 minus natural log absolute x plus 3, 0 to 2. We could use log property. If we want to use log property, we can. Let's do it. Might as well. You don't have to, but if you see it, sure, let's do it. It'll be a little easier to substitute it in. Plugging in the 3. 3 minus 5 is negative 2. So we're going to get negative 2 over 6. So it's negative 1/3. But then we take the absolute value, so we get positive 1/3. The natural log of a third minus natural log.
Is it 3?
You changed your bounds
Oh,
0 to 2.
to 2.
thank you.
That's what I was asking.
Okay, gotcha. Oops, I grabbed the 3 from the inside. Turning 2's into 3's. So, oh yeah, so that'll be different than here, right? Looks like it's going to be 3 over 5. Do we agree with that?
Okay, that makes sense.
More sense?
Yeah.
Good. Logic, it's a thing. And then when we plug in 0, we're going to have 5 over 3. Interesting. I'm disturbed.
Because it's negative.
I'm disturbed. What are we going to end up with then?
Like 0.
Right, 0. Does everybody see that? This is going to be 3/8, then we're going to have natural log of 3/5 divided by 5/3. Oh, no, it's not 0.
Oh, wait, no.
Yeah. We all were jumping to the wrong decision there. So it's 3/5 divided by 5/3. So it's 3/8 natural log. When we multiply by the reciprocal, 9/25. Okay, phew. Wow, it's funny. Several of us were thinking 0. Natural log of 1. Bad math. All right. 3/5 divided by 5/3 is 3/5 times 3/5. Any questions on that PFD?
Can you pull, so like when you plug in 0, you have 0 minus 5. Can you pull that minus sign out in front of the natural log? Is that where that went?
No, because of the absolute values, it disappears.
Oh, okay.
So when we plug in 0, we have negative 5/3, but then we take the absolute value of it, which is where the minus gets gobbled up. Let's look at a PFD with a nonlinear. Let's go down here. So there's a nonlinear. Let me just say something about this one. Let's not do this one. Let's just set it up. Is that x squared linear or is it quadratic? Say again? No. That is not quadratic. That is a linear factor that is squared. Right? We're thinking of it as x minus 0 squared. So it's a linear factor that's squared. It's not an irreducible quadratic. Right? So the setup would be a over x plus b over x squared. And maybe, so if it was x cubed, it would be a over x, b over x squared, c over x cubed. Everyone okay with that? All right, so those are linear. So think of that as a linear factor that's squared. All right, let's go to this more complicated one with a irreducible quadratic. So this one, definitely we have an irreducible quadratic. So we're going to rewrite this one as a over x. And then that irreducible quadratic, which should be the numerator?
Bx plus c.
Yeah, so we want to have a linear expression up here, so bx plus c. And then we're doing the whole cross multiplication, multiply by the denominator on the left, however you are thinking about it in your head. When you do that multiplication by the left-hand denominator, you'll end up with that. With an irreducible quadratic, it's best to use the traditional method where we equate the coefficients. Convenient values don't work so well with an irreducible quadratic because there is not a convenient value. You could use a hybrid approach, but let's just go through and do the traditional method here. It doesn't save that much time if we try to do some sort of hybrid and use convenient value to find one of the letters and then plug it back in, and it's not going to be that helpful. So we'll just go coefficient equating method, traditional method. So what is the coefficient of x squared on the left-hand side? 0. Coefficient of x squared on the right? A plus b. Coefficient of x on the left? 1. Coefficient of x on the right? C. Constant on the left? Constant on the left is 1. Constant on the right? 25a. So there is our system. We already have C solved for, so that's pretty easy system. So A will be 1 over 25, which will make B negative 1 over 25. Because A plus B has to be 0. Any questions on that part?
I have a quick question.
Mm-hmm.
So if you have like x squared plus 3 in the denominator,
Mm-hmm.
X squared plus 3 squared, do you write that as like,
X squared plus 3 quantity squared?
yes,
Yeah, so if we had another square, we would have to have another partial fraction
raised to a square?
raised to the quadratic factor squared.
Okay.
Yep. So now we can rewrite our integral as the integral of a over x. So a is positive 1/25. So 1/25 over x plus b, which is minus 1/25. So minus 1/25 multiplied by x plus c, and c we said was 1. All that's divided by x squared plus 25. All right. So, what do we get for the first integral? Let's focus on that one first.
Natural log.
Yeah, natural log of x. Absolute value of x. Now for the second one, what do you think we're going to do?
You're gonna do some factor it. No?
Split it. So we're going to split it. So let's make two separate integrals. So the first one will be negative 1/25 integral of x divided by x squared plus 25 dx. So that's the first one. And then plus 1. So plus integral of 1 over x squared plus 25 dx. So we're splitting the fraction. We're doing that first, factoring out the negative 1/25 out of the numerator, and then this second. What form is that integral in right there? Log if we multiply by 2. The derivative of the denominator is 2 times x. So let's do that. We're going to put a 2 up there. But if we put a 2 up there, we have to put a multiplication by 2 in the denominator out in front. Now it's in log form. Derivative of denominator is numerator. So we can then integrate it. This will be minus 1/50th natural log. We don't need absolute values here, though. X squared plus 25 is always positive. And then what's the plan for this last one? It's an arctangent, so I'm going to factor out that 25 in the denominator. So plus 1 over 25 integral of dx over x divided by 5 quantity squared plus 1. Factoring out that 25 puts it in arctan form. So we're going to have all this stuff out in front. And then we have to use reverse chain rule. So we're going to have 1/25th arctangent of x over 5 plus c. And what goes in our little RCR blank? 5. Derivative of x over 5 is 1/5. Dividing by 1/5 is multiplying by 5. And the only simplification we have here is that we could rewrite that as 1/5. Great. Any questions? Everyone see the fraction splitting piece? Super important. Fraction splits and we end up with a log and an arctan. All right. Improper integration. These are all about notation. If you don't use correct notation, you're going to be losing some points. So let's make sure that we understand each piece of this notation here. And the first piece of notation that's super important is that when we have an improper integral, you must take a limit. So an improper integral is the limit of a definite integral. So our very first step in almost every single improper integral should be limit of something. And in this case, our interval goes from 11 to infinity. So to make it a definite integral, we're going to go 11 to b, and then we'll let b go to infinity. So the limit as b goes to infinity of definite integral 11 to b. We're going to pop that x up into the numerator with a negative 1/2 exponent. Then we can use the power rule. So before we actually do the evaluation, let's think about whether we're expecting convergence or divergence. So for all of these reciprocal looking functions, 1 over x to the 3/2, 1 over x to the 1/2, for all of them, you are thinking something that looks kind of like that. And so are we finding a horizontal area or a vertical area here? Horizontal, we're starting at 11, so we're finding, this area of this unbounded horizontal tail. And are we expecting convergence or divergence when the power on x is 1/2 in the denominator? Divergence. If for a horizontal tail, power of x bigger than 1 in the denominator gives convergence. Power less than 1 gives divergence for a horizontal tail. For a vertical tail, power in the denominator less than 1 gives convergence. Power in the denominator greater than 1 gives divergence for a vertical tail. So we're expecting divergence here because this is a horizontal tail. So let's see, the process should confirm what we're expecting. So we're going to get x to the 1/2 divided by 1/2 from 11 to b. So first we evaluate the definite integral. The limit part just comes along for the ride. We'll evaluate the limit in a moment. We can pull the 2 out to the front. The 2 out to the front it's not going to change much here, but usually it's easier to evaluate a limit when there's not a bunch of extraneous multiplication division. So 2's coming out to the front. Plug in the b, we get square root of b. Plug in the 11, we get square root of 11. Let's make sure we're looking at the right limit. This is the limit as b goes to infinity. Square root of b goes to infinity. And infinity minus a constant, still infinity. And if we multiply by 2, still infinity. So that is telling us that this improper integral diverges. It's telling us that this horizontal area is infinite. So those are the things that we're inferring from this limit being infinity. So the notation that's important, this limit symbol, evaluating your definite integral and then evaluating your limit. So make sure you have the limit in there. You don't have to write as b goes to infinity every single time, but you at least have to write limit every time. Let's try another one since these are key. All right, so limit 2 to infinity, horizontal tail or vertical tail? Horizontal. If we see an infinity in the limit, in one of the limits of integration, we know it's going to be a horizontal tail. Okay, so immediately we write down the limit as b goes to infinity, 2 to b. The 9, that can come out to the front. We can bring it all the way out to the front if we want, way out in front of the limit even. Let me make a little more space there so it's more obvious. And then this is dx divided by x ln x. Okay. Now, this one is not just a power of x in the denominator. If it was just an x without an ln, would the horizontal tail be finite or infinite? If the ln was not there. So if it was just 1 over x. It would be infinite. 1 over x is infinite horizontally and vertically. It's when the power gets bigger or smaller than 1, that's what changes. So now, and we also know that 1 over x squared, horizontal, infinite or finite? Finite. 1 over x squared, we actually found that 1 to infinity gave an area of 1. So, this denominator is growing to infinity faster than x would grow to infinity because we're multiplying by something that's more than 1 most of the time, as soon as we get out a little bit. So the question is, does that ln of x cause the denominator to grow fast enough that the fractional values will go to 0 fast enough to get convergence? So we don't know. That's what we're finding out. Multiplying by natural log of x in the denominator, is it enough to create convergence? Let's find out. What technique for integration are we going to use here?
Log form.
It's not going to be log form because the numerator is not the derivative of the denominator. Right? So for log form, the numerator has to be equal to the derivative of the denominator. The denominator is a product. So its derivative is going to be, product rule. So what we're going to use is just u sub. And what will we choose u to be? If we choose u to be ln of x, that's a viable substitution if its derivative is present. And its derivative is present. The derivative of natural log of x is 1 over x, and we're seeing a 1 over x right in front. Right there, 1 over x. So this is going to be a good substitution. So let's see what we get. So this 9 and limit business, this just comes along. And we're going to put placeholder limits because with improper integration, it's usually just easier to use the original limits. So we're going to have a u in the denominator and a gu in the numerator. Now it's in log form. And maybe that's what you were referring to.
Yes.
So you were looking ahead.
Yes.
Yeah. You're moving too fast. So that's in log form for sure. So this is going to be 9 limit. That's going to be natural log absolute value of u. And we're going to have placeholder limits for a moment here. We're going to have 9 limit natural log of x. Ooh, this is getting fun. So we have that. And this is an absolute value here, so I need to make sure I keep that. That's natural. U is natural log of x, but this is natural log of the absolute value of natural log of x. Now, granted, from the interval 2 to b, that's all positive, so you don't actually need the absolute values there, but we should put them there for the time being. So then this will be 9 limit. Plugging in the upper limit of integration, we're going to get ln of b, and again, we can assume that's all positive, so we don't have to worry about absolutes, minus natural log of 2, and this is a limit as b goes to infinity. And what does natural log of b go to as b goes to infinity? Infinity. A natural log of something going to infinity is infinity. So this part definitely is going off to infinity. And if you subtract off a constant, that's not going to change anything. So we are going to get infinity. So therefore, we have an integral that diverges. So that function in the denominator, natural log of x, it's not enough to cause the fractions to go to 0 quickly enough for convergence. So it still diverges. All right, any step there you are wanting to ask a question about? All right, let's do a vertical tail. Should be able to get in one vertical tail. That's a vertical tail. That's a vertical. No, let's not do that one. Vertical tail. So here, again, it's not obvious because you don't see an infinity in one of the limits of integration. So it's not necessarily obvious that it's improper. But when you look at the limits of integration, one of them is 7. That causes division by 0, which means vertical asymptote at x equals 7. So that's our bad endpoint. So we're going to replace our bad endpoint with c. So we're going to go from c to 8. This is going to be our definite integral. And c is going to go to 7 from what side? So if our interval is 7 to 8, so 7 to 8, and we're putting a c in the middle, here's our definite integral from c to 8. c is going to 7 from the right-hand side. So approach 7 from the right. And again, we have something in the denominator. We just pop it up top. Make it a minus. As soon as we put it up there, then we can use the power rule. So this is a definite integral. The limit part just stays out in front. We add 1 to the exponent, so we're going to get x minus 7 raised to the adding 1 gives us a negative 1/4. Dividing by negative 1/4 gives a multiplication by negative 4. C to 8. No reverse chain rule here. If there was a 5 right there, what else would we have to do? Divide by 5. If there was a 5 coefficient on the x, then we would do reverse chain rule. But as it stands, the derivative of x minus 7 is 1, dividing by 1, no biggie. All right, so now we have, let's get that constant out to the front, just get it out of the way. So negative 4 limit. Let's also make that a positive exponent. It's going to be a little bit easier. So plugging in the 8, 8 minus 7 is 1 to the negative 1/4, which is 1 over 1 to the positive 1/4, which is still 1. 1 to any power. So that's what we get when we plug in 8 minus 1 over c minus 7 raised to the positive 1/4. So that's what we have. Okay. All right, so let's think about what's happening here. This denominator is going to 0. It's going to 0 through positive values. This c value is always a skosh bigger than 7. So a number slightly bigger than 7 minus 7 is always positive. So this is going to 0 through positive values. So 1 divided by a number approaching 0 through positive values, this part is going to go to infinity. Right? 1 divided by something that's getting tinier and tinier and tinier, but always positive, will go to positive infinity. But then 1 minus positive infinity, all of this is going to go to negative infinity. Right? 1 minus infinity, negative infinity. But then you multiply something going to negative infinity by negative 4. The overall limit will be positive infinity. So we will have an integral that diverges. So let's double check that that confirms what we would expect. So vertical tail, and the power on the x in the denominator is more than 1. Power on the x in the denominator more than 1 gives horizontal convergence and vertical divergence. When the power is bigger than 1 in the denominator, horizontal convergence, vertical divergence. This is vertical. We're getting divergence, so it makes sense. All right. Good luck. I will be checking email. I'll be checking the OneNote if you post anything in there. Checking Ask My Instructor. I'll check it all between now and then.